I'm talking about the fundamentals of selective laser sintering, which is quite an interesting application of powder-based printing technologies. And I'm talking more from a perspective of the industrial applications, less the pharmaceutical applications, because there are more degrees of freedom from the non-pharma side, especially for the powder engineering. And as you can see here, we talked a lot about binder jetting, and selective laser sintering is very similar to the binder jetting process. So we have a powder supply, we have a build platform. In both cases, we have a leveling roller or some kind of recoating mechanism. And in binder jetting, which we discussed in detail by now, we solidify the three-dimensional objects that we want by using an inkjet printhead and a liquid binder or liquid, whereas in selective laser sintering, we are using a laser to sinter the material and bind the material sinter together to a solid object. So I will really go more into the fundamentals because I was hoping on Jonas to show you a little more on the applications in a pharmaceutical sense. So please bear with me. So the general process looks something like this. To start a new printing process or to create a new layer, we move up the powder supply a little bit, as you can see here. We move down the build platform by the same amount or the same height, and then we recoat material. This means that recoating is the spreading of a new powder layer on the old layer, on the previously sintered on layer. Then we irradiate the powder bed with a laser, and then we have different processes that take place. First of all, we have an energy absorption where the laser energy is converted into heat energy. This heat is then transferred, and the sintering process itself takes place. And sintering in this context is understood as a surface melting process, which is leading to the formation of solid bridges. And after the sintering, the cooling takes place. And I will mostly talk about the recoating, energy absorption, and sintering mechanism. So here you see different options that you can have as a recoating mechanism. So if you want to apply a new powder, a new layer of powder, you have different options available. So Johanna Peters from Evonik was just talking about the voxeljet machine, and if I got it correctly, I think they are using a roller, a counter or co-rotating roller, where you add the powder or either put it directly on the surface of the previously printed layer, or as I said before, you move up the powder reservoir and then you scrape it over, you recoat it with such a roller system. And there are no general rules on which system is superior. It has been reported that a co-rotating, so this one in the middle, a co-rotating roller can lead to higher densities of the powder bed because you have a higher compression during the ongoing process, whereas you have a lower compression with this counter-rotating roller where the material is drawn upwards. There are some hybrid mechanisms that are possible that are able to create an even smoother surface, which is something that you're looking for. And if you don't have a roll available, so especially the cheaper benchtop machines for SLS have blades, different blade geometries selectable, and there are multiple geometries, of course, available. And there was one study that investigated the influence of the blade geometry on the homogeneity of the powder bed, so the smoothness of the surface and the porosity. And this study found that you have a smoother surface and a higher density powder bed with a flat blade geometry. And they say that this is because you have a larger horizontal contact zone between the powder and the blade, which allows for a more even compression of the powder bed. As I say, there is not one recoating mechanism that fits all, but if you have the option, it is reported that a rotating roller is superior to blade recoating mechanisms. Another very important property for the recoating is, of course, the flowability and the spreadability. This has been discussed before. And it would be quite simple to get a well-flowing powder. So what we want is a monomodal particle size distribution, spherical and rather large particle sizes because it just flows better. One issue that we have is that if we take larger particles, that the packing density will be reduced. And a higher packing density is actually quite important because in this case, we have a higher apparent density of the powder bed. We can get higher drug loadings, and we have also more contact points between the particles that can sinter together. So we get stronger materials. Another issue with larger particles is that they automatically increase the layer height. So we can take particles with a diameter of 500 micrometers as an X50, but then you will have layer heights in a very similar range and your resolution drops and also your feature size is decreased. So for a higher packing density, what we would prefer is either a rather wide particle size distribution or ideally a B-model particle size distribution consisting of large and small particles, as is shown here, where you can see that at a certain fraction of small particles in large particles, you have a maximum packing density. So this would be ideal for the packing density side. The downside of having a wide particle size distribution or a B-model particle size distribution with very distinct particle sizes is that the smaller particles have a larger surface area and therefore more surface and interaction potential with the lasers. So they absorb more laser energy, they melt faster, and then you have a very uneven melt generation on the surfaces of the particles. So this is quite unfortunate. So it's very difficult to strike the perfect balance between a good flowability and good spreadability and a high packing density. And this is something where the particle engineering comes much more into focus, which is also why I asked about the mechanofusion before, because we have very limited options from a pharmaceutical sense to optimize powders in a way as it is possible for commercial non-pharma materials. So Lena, you also asked the question before what the particle size, what the desired particle size is, and Johanna mentioned before that, well, target value should be around 50 micrometers, and the same is true for the standard commercial material. So it's polyamide with 12 carbon atoms, and there the X50 is usually around 60 micrometers, maybe 70 micrometers. It has a comparably small, a comparably sharp particle size distribution. But let's assume that you have found a pharmaceutical material that has a good flowability and spreadability and also fits packing density. Then you have to start with the sintering process. So here you see a small video of what the sintering process looks like on a machine from General Electric. And well, what takes place is you have the energy absorption, heat transfer within the particles and the layer, and you create a micro melt layer on top of on the surfaces. And what is the driving force behind the particles fusing together? So the free enthalpy of the powder. So the free enthalpy wants to decrease, of course. It's more or less a natural law that the free enthalpy wants to be as low as possible. And how is that achieved in this case? By decreasing the available surface area. So in this case, we usually get those solid bridges, which look somewhat like this, so concave solid bridges, sometimes called necking. And for the sintering process, we need mostly two different things. One is a laser, and the other is material that can absorb the energy. And of course, since you want to print with this process, we need a whole lot of equipment around it. But I will mostly focus on the laser and the absorbent for the next, I think, 2 or 3 slides maybe. So if you want to buy a selective laser sintering machine and you're thinking about acquiring one, you have a few options available on the market. So if you're thinking about getting a benchtop machine, they usually have diode laser around or below 5 watts of laser energy, and they have a laser wavelength below 1 micron, usually in the Vis spectrum somewhere. Those are the cheaper machines, by far the cheaper machines. So you can get a pretty good SLS printer with a diode laser for 4, 5, 6,000 euros. If you want to use a different machine, a CO2 laser, you have to pay significantly more money, so 40,000 euros. Then there is a very steep increase up to a couple of 100,000 euros, depending on what you expect from your machine. And the big difference with the CO2 laser is that the laser wavelength is in the IR spectrum. So the wavelength is usually 10.6 micrometers. But as you can also see here, the energy, the power is much, much higher. So 14 watts for a laser is already a lot, and 200 watts, you can cut through thin metal sheets with this. And just as a comparison, here you see the energy, the maximum allowed energy for a laser pointer, it's 5 milliwatts. So we are talking at least 3 orders of magnitude higher laser energy. And why am I talking about the different lasers, the wavelength and the energy? Well, because somehow we need to sinter our material, so we need to melt it. And for that, we need to convert this laser energy into heat that can be used to melt the material. And this can be measured, the amount of energy that is absorbed, as the absorptance, so the fraction of energy that is absorbed from a radiative energy influx, and it's equals to 1 minus the reflectance, so the energy that is reflected right away. So it's quite easy to measure the reflectance of a material, and then we usually know what energy we irradiate the material with, and then we can easily calculate the absorptance. And the absorptance depends on the wavelength of the laser, the material that you irradiate with it, the morphology of the particles, the temperature, the gas in the environment, and so on. So there are quite a few ways how you can tweak and optimize your absorptance. But let's go back to the laser wavelength lambda. So if you have a low laser wavelength in the visible spectrum, well, if you want to use a thermoplastic polymer, they usually, actually don't really absorb any energy in this light spectrum, which is also why if you look at the publications using a diode laser with a Vis wavelength, some colorant is added. So usually you have 1 to 5% of a colorant added, so comparably low relative volume and amount. And this little amount of colorant needs to absorb all the laser energy and convert it into heat, and then melt the surrounding materials. If you have a high wavelength, for example, with a CO2 laser, the energy is directly absorbed by polymers. So this is what is usually preferred, or would be probably preferred, for pharmaceutical 3D printing if you want to use thermoplastic polymers. And this also has a very big influence on the temperatures during the printing process. So if you have a low conversion efficiency, which I put simply more for the low wavelength and the visible spectrum, where you have only a low amount of colorant, you have a rather low conversion efficiency. So you need to have a higher print bed temperature and a higher surface temperature. However, if you have a rather high conversion efficiency, for example, with an IR laser, a CO2-based laser, you can run the whole process at lower temperature. And one issue that we also have with the higher temperatures, or generally elevated temperatures in this process, is that the polymer might age if you heat it up for multiple hours, because this is the standard time for such a printing process. And then the enthalpy relaxation might be very strong. And it's very critical if you can then recycle the material after usage. Talking a little bit more about the material, well, if you use a pharmaceutical polymer, you have options of using fully amorphous polymers or semi-crystalline materials, for example, a PVA. And this has some ups and downsides as well. So amorphous polymers have a TG, as you all know. So the material softens over a wide range. You have no defined melting temperature, and you heat your material in the printer to above the TG, and then you add the remaining amount of energy to melt the material sufficiently via the laser. A semi-crystalline material, on the other hand, well, it has a defined partial melt temperature. So this you can use to heat the material to just below the melting temperature of your semi-crystalline material. And then you can just use the laser to increase the temperature by a few degrees, melt the material, and sinter it together. On the other hand, you have the downside that with the semi-crystalline materials, that they like to recrystallize afterwards. And ideally, you want to have the whole material recrystallize at the same time, so you don't introduce any additional anisotropy. And for that, you usually have a hysteresis between the melting temperature and the crystallization temperature. And a very good process setting is defined, or process temperature is defined to be somewhere in the supercooling window. So below the melt temperature, but still above the recrystallization temperature during the cooling time. Independent of what polymer you use, you of course want to have a rather low melt viscosity, which is usually also better for the semi-crystalline materials. So let's go quickly about the process parameters. I already talked about the bed and the surface temperature. Then we can set the hedge distance during the printing process, which is also called scan spacing or line offset, and it's just the difference between the two different scans of the laser across a powder bed. So high hedge distance means that you have usually incomplete sintering and a rather weak structure if it's too far apart. And if it's too close together, you can have multiple passes on the same line and get over sintering and distortions in your print, and also very slow process. Then I already mentioned that we have lasers with different wavelengths, and we cannot change those wavelengths. So you set your print, this is set once you buy the printer, but what you can change is the power output. So you can either modulate it down, which might introduce laser instabilities in the energy output, which you don't really want, or you can use a beam splitter to reduce the energy, the laser energy, by a certain value, and then combine it ideally with the modulation to fine-tune the energy that you want to have. And you can control the laser scanning speed. And from that, you can calculate the surface energy density that you have on any given spot during your print by dividing the laser power by the hedge distance and the scanning speed. And this is a very intuitive equation that explains the laser energy input on the surface area. You can also use the overlay ratio, which is setting the beam diameter in relation to the hedge distance, which is part by now in the official definition of the surface energy density. And it has been found that the energy surface density correlates positively with the mechanical properties such as the Young's modulus and the elongation at break. But however, you cannot put more energy in there than as much energy in there as you want, because then you will have degradation and decomposition, whereas too low surface energy density is connected to a higher porosity. Then you can, of course, select the layer height based on the particle sizes that you use. And you can actually use the layer height to introduce it into the surface energy density function and make it a volumetric or volume energy density function. And it's also possible that you, if you choose the layer too high, that you have incomplete sintering, and therefore poor layer adhesion. So this is something that can take place, which you can control in a more sophisticated way. And one of the last points that you can optimize, and which has a very big influence into the mechanical properties of your print, is the build orientation. So you can print your object completely in parallel and horizontal, or you can print it vertically and have the layers in a completely different direction. You can print it at any angle offset, which is possible to optimize your mechanical properties. And unfortunately, there is no rule of thumb that you can apply to say that this is the best setting for this material, and so on, and so on, and so on. So it's very, very difficult to optimize this process, at least in pharma. So it's usually a very well understood technique, but in pharma, we are still missing the critical material attributes, the critical process parameters, and the critical quality attributes, even though there is, of course, some guidance from what is published in different industries and the pharmacopoeias. But the knowledge, there needs to be much more knowledge generated in this regard. And then I think it is worth to say that there are very sophisticated models for the powder recoating process, all thermal processes that are involved, the mechanical behavior of selective laser sintered part. So it's very easy to learn from other industries and other fields of research. And I think that this is a very promising technique for the manufacturing of pharmaceutical dosage forms. And Jonas would show you that this is actually the case, but now you have to trust me that it is possible to manufacture very nice dosage forms. So, well, I hope you trust me in this case. Thank you very much, and I'm looking forward to your questions.